Okay, so again, this is the last week of classes. And our third test is scheduled for next Monday at 3:30, the time of the final. So instead of a final, just our third test. And as I said, later today, I'll send out an email asking what other possible day we'll have a test, either Friday or Tuesday. You can ignore that if you're going to take it just the Monday at 3:30, the regular time. So really, the email will just apply to people who might want to take it at either a different time and or a different day. If you took the quiz and, as usual, just submitted it to me, your grade should be up on Blackboard now. GA said that he would have grades for everyone else tomorrow, so not today. Sorry about that. And also, as usual, the answers are on Blackboard. There are 3 versions, so make sure you're looking at the correct one. And sometime this week, I'll put it together so you're at class average on the Blackboard is what your actual class average is. So right now, it's kind of messed up. But again, it's pretty easy to figure out what you have because we have now all 4 quizzes. You're going to drop the lowest. That will be 25% of your grade. And then each of the tests is 25% of the grade. So if you want to figure out what your average is right now, then just get the average of the quizzes, get it out of 100, and then multiply that by each of the 3 grades you have by 25%, divide by 0.75 to make it out of 100. All right, so today we'll, kind of typical day after a test, we'll do a bunch of homework to start. And so I'm going to start with the one I kind of delayed for a couple of classes, which is in 4.2. So as you can see, it is, for some reason, rougher today. It's also, as you can see, making bigger corrections. I'm not sure why. Yes, so, right, so same thing. I usually, for whatever reason, use the A minus. So A minus officially starts at 89.5. And yes, so an A would start somewhere around 92.5. So, and so as I said, you'll have to let me know about read this. So 18 says, suppose we have a circle of radius 5. Centered at the origin where z is equal to y. So it is a circle that is at a 45-degree angle up from the xy plane. And we have our usual force field, just a really basic one. And we're starting at the 5, 0, 0, and going to the point 0 is 5 over square root of 2, 5 over square root of 2. So as usual for this type of thing, we have to parameterize the circle. And there are kind of 2 ways of doing it. One way is to use the definition of a sphere, which is just the distance of any point on the thing, setting it from a point, in this case the origin, to be equal to a constant, in this case 5. The other is to take the usual sphere, x squared plus y squared plus z squared, and equal to 25, and put in the z equals y. either form, we get this. X squared plus 2y squared is equal to 5. And we need to parameterize it, like usual for these types of things. Okay, so, somewhere you can kind of guess, which is this is now an ellipse. And so for an ellipse, we take something similar to it, the circular polar coordinates, and just adjust it. So x is going to be just exactly the same as usual. Sorry, that's a cos, cosine t. When I first came and I was looking for, there's usually a place in these types of things to change the thickness of what you're writing, but I don't see it anywhere. Well, sorry. And then for y, let's ignore z for a second because that's just going to be the same thing. We need it so that if I put in, oops, what am I doing? 25. I'm not sure where the 2 came from here. 25, of course. Is what do I need to, if I let x equal 0, what do I need looking for y to get the 25 and keeping it as a parameterization? Right. And then, of course, z is the same thing. So there's our parameterization. And because of the thickness, I'm probably not going to do the whole thing, but from there now it's the same thing. So I think this is the main question. What is our new parameterization? Because from there it's the same. Which is plug the parameterization into the f. That is an absolute value. Those are supposed to be just parentheses. So it is x y and z. And then r prime. So the derivative of r, which is just the derivative of each of these. The other question is, so it's then going to be the dot product. What are the limits? The question is, what angle is this at? In some ways it looks a little weird, but it's not too bad. Which is, if we're ignoring the z component, then the 5, 0 would be on the x-axis, and the 0, 5 over square root of 2 would be on the y-axis. So therefore, what is the angle? Right, pi over 2. Again, sorry about the writing. So then we would take the derivative, so we'd get the negative 25 sine cosine plus 25 over 2 sine cosine plus 25 over 2 sine cosine, which, does it come all up to 0? Can I check on something? Yeah, it looks like it might come out 0. Give me a second. I'm going to check on something. Yeah, not sure why. Let's check, but so this one actually, it's going to say, I'm not going to have room to write the answer, but I am because it's just 0. So any questions on this? It's conservative. Yeah, so we should be, I think. Yeah, so we should be able to just get the potential function and plug in the numbers. So first in the background, you're not going to see something like this. As I said before the quiz, for the test will be similar, which is the only ones that you have to get the parameterization for are lines and circles. But the idea is, basically what we were just doing is saying, well, what do we plug in for x to get the 25 part of it? So that's where the 5 comes from. And then for the y, what do we plug in to get the 25? And that's 5 over square root of 2 to cancel out the 2 in front of it. Oh, and yeah, I say circles, but spheres are possible, slightly possible also. So any questions on this? Being a little almost nostalgic. This almost looks like an old school video game writing with the really bad scale and stuff. But any other questions on this? Okay, so let's look at 4.3, which kind of goes with the one question about the conservative part. So here's a force field. And in 9, they kind of split this question up in 2 parts. Yeah, I know, sorry about that. 3, so it is y squared plus 2xy cubed, and then 2xy plus 3x squared, y squared. Sorry about that. I said it's correcting more than even usual. So for example, I just changed my c to something completely different. So is this conservative? That's supposed to be p and a q above the 2. So what has to be true? So what for the quick check, what do we do in terms of p and q? Let's take the derivative of p with respect to y. which is not sure why I have parentheses around it. 2y plus 6xy squared. And qx. Is also the same thing. Okay. Second part of 9 says, well, if it is conservative, find the potential function. How do I find the potential function? Right, but we're taking it with derivative with respect to x. So that's why it was 3x squared. So the square went away for the x. So how do I find f? So I take the derivative, for example, of p with respect to x, which gives me x y squared plus x squared y cubed. And then I might be missing c of y. Is also equal to the derivative of q with respect to y. So now I take the derivative of q with respect to y. And in this case, I get the same thing. And then remember that when you put it together, take any term that you have, just don't take any term that's repeated more than once. So we have xy squared twice, but we only get one of them. Same thing for x squared y cubed. So the sum will be any term in either of the antiderivatives, just none of them doubled. And you can double check because now the gradient of this should be equal to what we have, the original force field. So any questions on this? Okay. 17 continues the problem. It says, suppose we have this same force field. And we're going to look at the force, the work move along this curve. That's supposed to be an I. I'm gonna have to read off everything because it's really mangling my writing. So First, we're going from negative 1, 0 to 1, 0 along the circle. And then along from the point 1, 0 to the point 1, 1 along a line segment. Same as in 9. So this is the same from problem, same force field from problem 9. And then the C is these pieces. And finally, we go from 1, 1, 1 to the point negative 0, again along the line. And so we want to find this. And I'm going to write this down, but you're going to tell me in a second why we don't need it. So that the conservative part says that we're going to get 0. So I don't need to write this integral. But the conservative part says that the integral of, or the line integral of the force field is equal to the potential function from our starting point to our ending point. And it doesn't matter what happens in the middle. So in 17, they have purposely made this a fairly complicated path just to check to make sure you know, well, none of it really matters. The only part that matters is we're starting at 1, 0, negative 1, 0. We're ending at negative 1, 0. So if it is conservative, the path doesn't matter. All that matters are the two endpoints. And the way you do the line integral is find the potential function and plug in the two endpoints. In this case, we don't even have to find the potential function, because since we show that it's conservative, we know we're going to get the function at the starting point minus the function at the ending point minus the function at the starting point. And since those are the same, we're going to get 0. So for 17, all we had to do was show it was conservative. We didn't actually have to get the potential function. So any questions on this? This is the main part. Okay, so let me do another one. So this is for a two-dimensional one. Let's try it for 3. Trying to write slower so it doesn't change things quite as much. So we have this, And again, the first question is this conservative? So to be conservative, what do we need? In some ways, there are a few parts that, right, so we need what we had before, and then the extension. We need all the mixed second derivatives to be the same. So if this really is the gradient of a potential function, then derivative of p with respect to y should be equal to derivative of q with respect to x. Derivative of p with respect to z should be the same as the derivative of r with respect to x. Derivative of q with respect, and I'm going to write this in a second, derivative of q with respect to z should be equal to the derivative of r with respect to y. So all the mixed second partial derivatives should be the same. And one way of doing that, although we need it explicitly here, is we can get the curl. We won't need this explicitly until 4.7, but you can use it now if you want. So that's just subtracting all the mixed second derivatives. And if it's conservative, this will just be the zero vector, just showing that mixed second derivatives are the same. So we need the derivative of r with respect to y. Just minus sine z, minus the derivative of q with respect to z, which is the same thing. Derivative of p with respect to z, minus the derivative of r with respect to x, both zeros. Derivative of r with respect to oh, that's a q. Can't even read my own writing. So yes, this is it. This last one here is a q. Q with respect to x. So they're all zero. So all the second derivatives are the same. So which means it is coming from a potential function, which means it is conservative. And that, of course, now means that we can now find, and I'm going to leave it so see if I can actually fit it in, is let's actually get the potential function. And so this time we're going to take 3 antiderivatives and again get the common parts. So take the derivative of p with respect to x, like in the last one. Take the derivative of q with respect to y. That's y cosine z. And then take the antiderivative of r with respect to z. So that's a y cosine z. C of that matters too much, but yz. And then again, we just take anything that's come up once. So we have an x sine y. We don't care that there's two of them, so we just write the ones. We have a y cosine z. Again, we have it twice, but only write it once. And then e to the z. In the text, what they're doing with these is a little bit different. What they're doing is doing the first one, taking the derivative, setting c prime equal to it, and so it's basically the same thing, just worded a little bit different. And now if I wanted to find the work to move along a path of the given force field at the top, all I'd have to do is plug in the two endpoints into this new function. So for example, if I went from 0, 0 to 1, 1, 1, it would be sine of 1 plus cosine of 1 plus e minus 1. So again, once we get the potential function, the way to use it is just by putting the two endpoints, and we don't care what the path is. So any questions on this? So those are the two I wanted to look at. Any others from 4.3 that you have questions on? Okay, so 4.4, which we did one example of. Let me do one from there. And I think I have to fill in one thing. So this is Green's theorem. So after I present the problem, I'll remind you what 4.4 is giving us. So actually, I should have done it before, but that's okay. So here we have this is our force field. And our C is we're going to move along a circle of radius 2 in the clockwise direction. And we're going to go the full circle. From 4.2, we know that it doesn't, I think I said this, it doesn't matter where we start. If it's a closed path, we can start anywhere on the path. So Green's theorem says is the boundary of some region R is closed path, is in the counterclockwise direction, then given f is equal to PQ, so just a two-dimensional one, the line integral of f is equal to the double integral over R of the two-dimensional curl, Q of x minus P of y. So the part which I don't think I gave last week is this part, which is, since if I reverse the order I get the negative, I do have to say which way is the basic one. So in this case, it is counterclockwise. So the fact that here we want to go along the path clockwise means once we set up the integral, we're going to have to put a negative in front of it, because if you go the opposite direction, you change the sign. So the first little thing is you should check to see if this is easy, because we know since it's a closed path that if it's conservative, the integral is going to be 0. So is this a conservative function? So here's again our P and our Q. No, because Q of x is equal to 2y plus 5. P of y is 2y. So it almost is, but not quite. So therefore, we can use the fact that the one we want to get, so I draw my little path, circle in the clockwise direction, and there's our R. So Q of x is P of y is, so in some ways, if we wanted to use Green's theorem, we'd be getting this anyway, so we're sort of checking to see if it's conservative anyway. Derivative of Q with respect to x is 2y plus 5. Derivative of P with respect to y is 2y. That's 5. And therefore, the integral of f on c is equal to the double integral of R, the disk, of 5. And here, this is going to come up a lot here and in the following sections, which is if you integrate a double integral in terms of a constant, you get area. And that means you do not actually have to do the integral. So if we're actually going to do the integral, we would probably use polar coordinates, but we don't have to. We just need what is the area of R. Or say circle of radius, and I'm going to add in one little thing in a second. Circle of radius 2, so therefore its area is 4 pi. So this is 20 pi. Again, it's straightening out my lines. But this is where the direction matters. The theorem says these are equal if we're going in the counterclockwise direction. We're going in the clockwise direction, so therefore we put a negative in front of it. So we get negative 20 pi. 4 pi is the area of the circle. So it's a circle of radius 2, and then we have area is equal to pi r squared. So pi times 4. Normally I would put that in, but I'm trying to keep it on the one page. So this is the basic idea, which is if we have a closed path, instead of doing the line integral, we can do a regular two-dimensional double integral. And this is fairly typical for test type questions, which is we could do this using line integrals, where we'd have to parameterize the curve, which is the 2 cosine theta, 2 cosine t, 2 sine t, plug it in, take the derivative, do the dot product and everything. But you can see this one's easy because even as we set up the double integral, we don't actually have to do the double integral. So any questions on this? Okay, so let me do one more. So there's our force field. Our path is we're going from the origin to this point along the line. We need to know the direction. I'll put in the direction that we are going counterclockwise. Then we're going to follow this circle to 0, 1. And then we're going to follow the axis back down to 0, 0. So again, a closed path. And again, since it's closed, it makes sense to check, is it conservative? And since if it isn't, we're going to use Green's theorem. We might as well just get what is q of x minus p of y. Again, that is p is q. So derivative of q with respect to x is x squared minus the derivative of p with respect to y is minus 3y squared, so we get this. So our r is the inside function. So the integral of c, which is the path of f with respect to r, is equal to the double integral over r of this 3x squared plus 3y squared. This one isn't quite as nice as the last one, so it's not quite as obvious that this is better than just doing it the way from 4.2. But if we were going to do it, what coordinate system would I use for this? Because we're moving along a circle, we would be using polar coordinates. And then 3x squared plus 3y squared becomes 3r squared, and then we get the extra r, as always. R goes from, and I didn't really give myself enough room for that. outside ones, 0 to 1. And then we need to know what are the two angles. The smaller angle is pi over 4, because it's y equals x. And the top is pi over 2, the y-axis. Okay. Let me talk about 16, but not really do it. 16 says we have a similar picture. F is the same as in 9. And we start the same way. We go to the same point, which I'm not going to write because it's messing it up anyway. And then go to 0, 1, but just those two pieces. And the idea is, again, get the line integral over C. So certainly we could use the 4.2 method, which is parameterize C1, which is y equals x. So therefore, it would be r is equal to 1 over square root of t, 2t, 1 over square root of 2t from 0 to 1. Plug that in. Parameterize C2, which is cosine t comma sine t from 0 pi over 4 to pi over 2. And again, do the same thing there. Or just give an alternate if you want. We can add in C3. And then we can use the fact that the integral over C is going to be the integral over C plus C3 minus the integral over C3. And the reason we might want to do that is C3 you can see is a pretty easy one because x is 0, so things are going to simplify a fair amount. And the parameterization is just something like 1 minus t for y. Or here I probably use y equals t, just t goes from negative 1, from 1 to 0, so kind of backwards. And then the derivative would be 1, and we would just get something like t to the 6th. I'd have to go through the whole steps. But the idea is it gives us an alternate, which is this part is closed. So therefore I can use Green's theorem to get that part. And this part is fairly simple. Doesn't mean it's better, it just gives us options. So I'm not sure which one is actually easier, doing it directly or using Green's theorem. But in another case, it might be more obvious. So for example, if the force field was such that the two-dimensional curl was a constant, then it probably would be easier because we wouldn't have to do the integral for the C plus C3. So any questions on this? So the first 9 is just another closed one, and then 16 is saying, well, if it's not closed, if it's almost closed, it might make sense to close it, and then use Green's theorem on that part, and then subtract off the piece that we added. So any questions on this? So what I'm going to do now is have you try one of each, 4.3 and 4.4, and then come back and we'll probably start at least quickly. Yeah, because it's fairly early. The next thing. So here it is. So I'm going to stop recording because it's going to be the usual